So now let's see how we can take this math that we wrote out for just 4 nodes and just the last step of 4 nodes and see if we can generalize it to more than just 4. So I'm going to write C of S and I along the same lines as the pattern of what's above to mean the following. So this is going to be the minimum cost of a path starting at node A, ending at node I, so ending at node I, passing through intermediate nodes S, so S is the set of intermediate nodes, right? So that's that. And what we see is that this is going to be the minimum over S, right? So the minimum out of all of the nodes in S, right, where we say, okay, the nodes in S are the nodes that we pass through. One of those has to be the second to last node we pass through. So let's go check all of them to see what happens if any of them are the second to last. So the minimum over S, so we'll index the set S with J in this case. And now we can just do the same thing that we have above. So what do we have above? We have the cost of S excluding node J, right? Excluding the node that we're kind of hypothesizing could be the penultimate. So S minus J, okay? And then ending on node J, right? And are we done? Well, no, we still have to add in the distance, right? So this is the cost of that subpath plus the cost of going from the end of the subpath to I, which is just simply dji, right? The path of going from that node to that node. All right. So that's the DP idea for this algorithm. So that captures it. So let's ask ourselves now, what is the complexity of this algorithm? And so what I want to do first, right, before I show you the right way of doing the complexity, I want to show you the wrong way of doing the complexity. And I know this is backwards, but what happens when you're working on these things is you'll see a path in front of you and you'll say, this might lead me to the answer. And then you'll follow that path to something. And if it feels like it could be the answer, sometimes you're tempted to stop. So what I want to do is I want to walk you through that process, take you down the wrong path to start with to something that looks like it could be the answer, and then show you kind of in this instance what it means to say, hey, wait a minute, that doesn't quite square with what I would expect here. So let's think about how we would analyze the complexity of this thing. So this is intrinsically it's intrinsically recursive. So you might think about trying to build up a recursion tree or a recurrence relation that captures what's going on here. So let's think about what that does. So we want to look up the complexity of this thing. And the first thing we want to do is an incorrect, naive approach. All right, so what are we going to do? Well, to solve this, right, to solve C of Si, so to solve this subproblem, C of Si, I need to solve as many subproblems as there are nodes in this set, right? So I need to solve essentially this many subproblems, okay? And so as we're building our recursion tree and setting up our recurrence relation, we should expect to see at most that number show up. Okay, so let's, just for the sake of argument, let's build a recursion tree for our simple 4-node example. So recursion tree for the 4-node example. So in the 4-node example, the big question that we're asking is, what is C of B, C, D, and A? Right? That's our big question. That's the overall question. And what we showed here is that to solve that, we have to solve 3 subproblems. Okay, so we have to essentially imagine recursing 3 times. And what do we recurse on? Well, we recurse on C of CD and B, right? The one where the penultimate node is B. We recurse on C of B, D, and C. That's the one where the penultimate node is C. And we recurse on C of B, C, and D, where the penultimate node is D. So now let's think about what each of these look like, right? So now our recursion tree is just split into 3. What we just said is that every time we recurse, we have to solve as many subproblems as there are nodes in our set description here, as many nodes as there are intermediate nodes in our paths. And so that means that each of these 2 is going to split into 2. Right? So this one is going to split into C of D and C, and C of C and D, right? Either C is penultimate or D is penultimate. This one will split into, I better write smaller here, so B and D, or C of D and B. And this one will split into C of B and C of C and B. Okay, those are the possibilities here. And then once we're at these, what do we need to do? Well, notice what we're asking here. So suppose I'm looking at this one. Here I'm saying, what is the optimal cost of a path that starts at A, ends at B, and then has exactly one intermediate node, and we'll call that node is C. Well, that's a trivial question, right? That's just go look up the distance from A to C, and then go look up the distance from C to B, and that's your answer. So for all of these leaves, when there's only one thing in the set of intermediate nodes, all of the as there is in all the leaves on this tree, there's no problem to solve, right? The problem is the answer is just given to you. There's only one path from A to B that goes through exactly one node C, right? And so we just return the cost of that path. Okay, so this is that means this is the complete recursion tree. So let's see what's going on here. Well, we've got n equals 3 here, right? If you like, we're asking for a path of length 3 or 3 plus 1, and then we've got an n equals 2 here, n equals 1 here. So let's think about what it would look like to build this into a recurrence relation that captures this recursive structure. Okay, so notice that when n equals 3, we split 3 times, and we recurse on a problem that is one less. When n equals 2, we split 2 times, and we work on a problem that is of size 1 less. Okay, so that tells us that the recursive part of our recurrence relation will look something like this. So t of n, which is going to represent the root of this recursion tree, says if I have n intermediate nodes, I have to recurse n times, right? That's just because that's how many intermediate nodes there are. So that's n. Now times t of what? Well, every time I recurse, I shrink my problem size by 1. So if I start out with 50 potential intermediate nodes, the first time I recurse, I'm going to say, well, now I'm going to consider paths that are length 1 less, right? So that would be 49. So this is n, t of n minus 1. And then the question is, what happens once I'm done with this? Like, once the recursion is done, which is captured by this piece, what do I have to do? Well, I have to compare n numbers, right? So that is, very strictly speaking, that'll take n minus 1 comparisons. But just to keep the math simple, and because it doesn't end up making a difference, I'm just going to write n right here. So this is to compute the minimum of all of the returned answers to the subproblems. Compute min of n numbers. Okay, so there's our recurrence relation, right? We should be savvy enough to be able to solve this thing. So let's kind of think through what the solution of this thing is going to look like, or at least let's think through what a lower bound on the solution of this thing is going to look like. So there's our recurrence relation. What are we going to work with? Well, you might as well use kind of a repeated substitution approach here. So I'm going to write t of x equals x, t of x minus 1 plus x. And what I want to do is compute t of n minus 1. So plug n minus 1 in here, and I get t of n minus 1 equals n minus 1 times t of n minus 2 plus n minus 1. So then I substitute that back in, and I get n times n minus 1. And let's be careful about brackets and make sure that we keep track of everything we've got going on here. So I plug this in, and I have n minus 1 times t of n minus 2 plus n minus 1 plus n. And so what does this look like? Well, this looks like n times n minus 1 times t of n minus 2 plus n times n minus 1 plus n. Okay, so as a first step, we seem to have a huge blow up in the complexity. Okay, why do I see a huge blow up? Well, because I went from having to solve n subproblems that are almost as big as n to now having to solve n squared subproblems that are almost as big as n, right? Just marginally smaller than the original problem I started out with. So I won't go into the details of how this works, but the next step takes us to something that looks like this. So it looks like n times n minus 1 times n minus 2, okay, times t of n minus 3, whoops, plus a bunch more stuff, right? So plus n times n minus 1 times n minus 2, plus now everything that comes from this term, which is n times n minus 1 plus another n. Right, so this is looking rough if you wanna prognosticate a little bit. And so notice what's happening here in particular, right? Even ignoring the rest of this, what's happening here is that every time we recurse, we multiply on another n, essentially, and we have a problem that has been shrunk a little. So what happens if you multiply on n with these numbers subtracted from it? Well, this whole thing starts to look like n factorial. Okay, so what does that mean? Well, that means that since one of the terms here is n factorial, it appears that the others are going to be as well, but one of the terms at least is n factorial, so this whole thing has to be big omega of n factorial, right? At best, this algorithm that we've derived, and at least as we have understood its complexity, at best it is an n factorial algorithm. So the question remains, what went wrong? Right, so we were hoping to find some kind of cost savings, relative to exhaustive search, but this analysis that we've just performed suggests that we actually didn't. That we might as well just do exhaustive search because this is giving us an n factorial complexity. So the question moving forward is what went wrong here? Or did something go wrong, right? Or could we actually, ascertain that sure enough, this thing actually is a factorial algorithm? I'll just give you the sneak preview. It turns out it's not. Turns out it's much better than factorial. It's not sub-exponential, but at least it's better than factorial. And that's what we'll analyze and reason about in the next set of videos. But the issue here is that what we did is we did this DP algorithm that's supposed to save us work, or ideally would save us work if it was executed correctly, and yet somehow we ended up with something that wasn't better, and in fact appears to be worse than the exhaustive search algorithm. So that should tell us, that should make us feel uneasy. Something shouldn't sit right about a result like that. Right? We should get some algorithmic improvement if we do something smart with our algorithm.